Hey there, and welcome. Have you ever stopped to wonder how doctors, in the middle of all the chaos, nail the exact right dose for an IV drip? Well, believe it or not, scientists have this surprisingly simple way of looking at it. They basically pretend your body is a bucket. Yeah, a bucket. And today, we're going to dive into this powerful idea. It's called the one-compartment model, and see just how it helps save lives. All right, so first things first, let's set the scene, because this is really where it all matters. I want you to picture a high-stakes, high-pressure ER, where every single second counts and every decision could be life or death. So really think about that for a second. Someone comes in with a major infection, maybe a heart attack. You've got to get that life-saving drug into their system, and fast. But how do you figure out the perfect amount? I mean, give too little, and it's useless. Give too much, and you could do serious harm. It's a real Goldilocks problem, right? Not too much, not too little, just right. And that is the exact problem this whole bucket model was designed to solve. Okay, so how do we get from a complex human body to a simple bucket? Well, this is where pharmacologists did something kind of brilliant. To make sense of all the chaos and complexity inside us, they start with a really, really bold simplification. They basically decide to treat the entire body as if it's just one big, well-mixed container of water. And this idea right here is the foundation of the whole thing. It's called the one-compartment open model. Now let's break that down. One compartment is exactly what it sounds like. We're pretending the body is one single container. It has a certain volume, which we'll call VD. And the open part, that just means the drug doesn't stick around forever. It's constantly being removed or eliminated at a specific rate, which we'll call K. So, bottom line, drug goes in, it mixes around, and then it starts to drain out. Now, I know what you're probably thinking. Wait a minute, that's not realistic at all. And you're right. Scientists know this isn't a perfect picture of reality. A drug doesn't magically mix across the entire body in a split second. But, and this is the crucial part, by making these simplifying assumptions, the model becomes this incredibly powerful tool for predicting how a drug's concentration is going to change over time. And that is exactly what a doctor needs to know. Okay, so if we're running with this bucket analogy, the very first question we have to ask is, well, how big is the bucket? But here's the twist. We're not talking about your actual physical size. We're talking about the space the drug seems to spread out into. And this is where the concept gets really, really cool. It's called the apparent volume of distribution, or VD for short. The key word here is apparent, because it's not a real anatomical space. You can't point to it. It's more of a theoretical volume. Think of it like a handy mathematical tool that connects the amount of drug you put in to the concentration you can measure in the blood. So how do they even figure out this VD? Well, the math is actually super straightforward. Let's walk through it. Say you inject a known dose. We'll use a nice round number, like 1,000 milligrams. Then, right away, you take a blood sample and measure the drug's concentration. And let's say you find it's 1 milligram for every milliliter of blood. All you do is divide the amount by the concentration, so 1,000 divided by 1, and you get 1,000 milliliters. Boom. That's your volume of distribution, 1 liter. And this isn't just a theoretical number. It tells you so much about where a drug goes in the body. Check this out. Take a drug like warfarin. It has a really small VD. Why? Because it loves to stick to proteins that are already in the bloodstream, so it pretty much stays right there in the blood. But then you have a drug like digoxin. Its VD is, wait for it, enormous. We're talking a volume that's technically bigger than a person. So how's that even possible? Well, it's a massive clue that the drug isn't hanging out in the blood at all. It's left the bloodstream and is binding up all over the place, in tissues like your muscles. That makes it look like it's been diluted in a gigantic bucket. All right, so we've got a handle on the bucket size. That's VD. But remember what we said earlier? This is an open model, and that means our bucket has a leak. That leak is your body doing its job, metabolizing and getting rid of the drug. So the next logical question is, how fast is that drain? So what you're looking at here is a classic picture of what happens after a drug is given all at once. It's called an IV bolus. And it's pretty intuitive, right? Right at the beginning, the concentration of the drug in your blood is at its peak. Then, as time goes on, it starts to drop and drop and drop. That downward curve, that slope, that's your body clearing out the drug. And it makes sense. The steeper that line is, the faster the drug is leaving your system. Now, there are a couple of ways to talk about this drain. The first one is a bit abstract. It's called the elimination rate constant, or just K. The best way to think about K is as the fraction of the drug that gets removed over a certain period. So for instance, if a drug has a K of 0.1 per hour, That just means that every hour your body gets rid of 10% of whatever drug is left.
Okay, but honestly, there's a much more intuitive way to think about this whole process, and it's a concept called clearance. What's cool about clearance is that it shifts our focus. Instead of thinking about the amount of drug being removed, we start thinking about the volume of blood being cleaned. This image here does a great job of showing the different ways you can look at this. You could focus on the mass of drug leaving the body, which is A, or you could focus on the fraction that's leaving, which is C, that's our buddy K. But for a lot of reasons, the most useful approach is often B, clearance. Thinking in terms of the volume of blood that gets scrubbed clean every single minute. And here is the absolute key takeaway about clearance. For most drugs, it's a constant. Think of your kidneys and liver as a filter system. That system is always processing the same volume of blood hour after hour. Now, sure, when the drug concentration is really high, that filter will pull out a lot more of the drug. And as the concentration drops, it'll pull out less. But the volume of blood it cleans every minute, that stays the same. It's a constant.
Okay, let's pause and put it all together. We have the size of our bucket, that's VD, the volume of distribution, and we have the speed of the drain, that's CL, or clearance. So what's the big deal? Why are these two seemingly simple numbers so incredibly important in medicine?
Well, this is the payoff. This is where it all comes together. Because if a doctor knows just those two values, VD and CL, they can basically predict the future. They can predict what the drug concentration in a patient's blood will be at any time. And that means they can calculate doses that are safe and effective. It helps them figure out exactly how long a drug will work, and it prevents levels from getting dangerously high. It's what turns dosing from a guessing game into a real science. And it all comes back to that simple, powerful idea of a bucket. So there you have it, the one-compartment model. It's this incredibly elegant way to understand and predict what a drug does in our bodies, just by thinking of it as a bucket with a leak. But of course, that beautiful simplicity leads to a bigger, more complicated question, doesn't it? What happens when the body isn't one simple compartment? What happens when it's more like a whole series of interconnected buckets? Well, that's a story for another day. Thanks for diving into this with me.